hormone is binding to its receptor. You can imagine that you must have shape complementarity, like this represents shape complementarity. But in addition to having a matching geometrical surface, you have to have a little bit of glue in there to make it stick, otherwise it just bounces away. So here's a molecule, actual X-ray crystallography data on a protein. This is the protein surface, and showed in a slightly different way is a small molecule that binds to the binding site on that protein. It has structural complementarity, like this, but it's also only going to stick to that surface if there's something like a bunch of hydrogen bonds or hydrophobic interactions and so on. So you need both structural complementarity and weak interactions. Here's the hormone binding case. These are insulin receptors. Here's the surface of the cell. On the outside of the cell, you have these insulin receptors, and the blue, that's insulin coming in and binding to a specific part of the molecule. So they switch colors in this picture. This is the insulin receptor. This is an insulin molecule coming in and recognizing it and binding to it. So for this system to work, you have to have structural complementarity on the surface that matches the shape of the insulin. It must have some stickiness to it, so that's where the weak interactions come in. But those interactions can't be real strong. It can't be covalent. If insulin came in and attached through a covalent bond that took 300 or 400 kilojoules per mole to break, it's going to come in and it's never going to leave. So if this is a liver cell, it's just the surface of which has just been activated by insulin. If it's a permanent strong bond, okay, your liver is switched into, the insulin activated mode forever. The idea is that a lot of these molecular interactions are meant to be short term. So you need it to fall off. You need it to stick enough that it can stick around and do its job but not be permanent.